Alexa, quiet. Alexa, stop. I'm going to have to record you. Right. Lesson 84. Are we recording? Yes, we are. You might have recorded me shouting at my Alexa, politely, asking her to be quiet. Right, lesson 84, page 522, 19.2, statics. 84 or 86, mechanics lovers, we're getting there. Statics is the study of forces in equilibrium. In the previous chapter, we learned to resolve forces in motion. However, if an object is in equilibrium, then the resultant force acting on it is zero. Imagine a book resting in equilibrium on a table. If we apply a horizontal force P to the book and it doesn't move, then friction is acting to oppose P and F equals P. Okay, as we increase P can be a push or a pull, and the book still does not move, the friction F increases in line with P, but only up to the point where the book is on the point of moving. At this point, F has its maximum value, which is called limiting friction. So basically, there's so much friction that you've got to overcome before the book starts moving. If P increases further, the book moves. So if we repeat this with different books, we'll find the limiting friction changes. It's proportional to the normal reaction R. So the limiting friction F is mu times R, where mu is the coefficient of friction. The rougher the surface, the greater the value of mu. However, if the book is not on the point of moving, then F is less than mu R. So key point, friction acts to oppose motion. Friction F and the normal reaction R are related by F is less than or equals to mu times R, where mu is the coefficient of friction. When the object is about to move, it is in limiting equilibrium. And limiting friction F is mu times R. Okay, I like to do examples of these. And here is one. A crate of mass 50 kilograms lies on a rough horizontal table. So there's your crate, 50 kg. Okay, so straight away from the centre, we've got 50g downwards. And then we've got the normal reaction upwards. Okay, 50g is 50 times 9.8, which is 490 newtons. Okay, a string is attached to the crate and pulled at 20 degrees above the horizontal until the crate is just about to slip. So we've got a pull and it's 20 degrees. Okay, so this way we've got P cos 20 degrees horizontal, and then we've got P sine 20 degrees vertical. At this point, the tension in the string is 200 newtons. So I can change that P. I'll change that to T for tension, which is 200 newtons. You can call it P if you want, but it's called tension, so I've changed it to T. Find the normal reaction R and the coefficient of friction mu. Okay, so the friction comes in here. Friction opposes the motion, so it's in the opposite direction from the pull. And friction is mu times R. Okay, I don't feel like I've left myself enough room for all these. So that's all the forces. It's always useful to put one of these diagrams in. Okay, we've got horizontal forces and we've got vertical forces. Okay, so I'm having a quick think here. I've put P there for the pull, which changed to T and changed to 200. So I'm going to change them to 200. Okay, so let's have a little look through. We've got, that's going to be a value, that's a value. In fact, I'm going to do these different colours. I'll do the upwards ones and the vertical one, the horizontal one's different. That's a vertical one. That's a vertical one without a value. That's a vertical one with a value. And then we've got the friction, and that's a horizontal one, so yellow. So it's just on the point of moving. So all these forces are in equilibrium. And let's start with the horizontal ones. Nope, let's start with the vertical ones. If we start with the vertical ones, because I was just having a quick look there, which are the green ones. Are we in green there? Green. If we look at these vertical ones, because we've got R plus 200 sine 20, they're the upwards ones, equals the downwards one, 490. Okay, so that means we can work out R. The reason why I started with the vertical ones is because the horizontal ones, there's two things to work out, mu and R. Whereas vertical, there's only one R. And then when you work out the R, you can use it in the horizontal one as well. Okay, so R is 490 minus 200 sine 20. This is degrees, make sure your calculator's in degrees, which is 188 newtons. So 3 significant figures. We only really need 2, but it doesn't matter. We've got R is 188. So that's 188 newtons. And the important thing here is that we can write F is mu times 188. So now if we do the horizontal ones, I'll do it in this bottom corner here, just because that's where the space is. And these are going to be the yellow ones. We've got 200 cos 20 degrees minus mu times 188 equals 0. Okay, because the forces to the left equals the forces to the right. So mu is 200 cos 20 degrees divided by 188. I'm just a bit worried that I made a mistake there. 200 cos 20 divided by 188, 0.99999. Just going to check with the book. R plus 200 equals 290. I've just done it in a slightly different order from the book. 490 minus 200 sine 20. I made a mistake there when I do that on the calculator. That comes from not looking at my notes properly. R is 421.6 newtons. Sorry, it's 422 newtons. I'm rushing. Okay, yeah. So I don't know where I got that. Yeah, that was just calculator error. Got to substitute that into the calculator, and you definitely get that. So horizontal, you've got 200 cos 20 minus mu times 422 equals 0. So mu is 200 cos 20 divided by 422. Uh, 0.445. 0.45. So 2 significant figures. Okay, so yeah. Right, next one. Lamy's theorem. If we've got 3 forces, A, B and C, act on an object that is in equilibrium. there's the object. Got one force that way, one force that way, one force that way. So it's A, B, and C. Okay, e.g. dogs pulling on a post. For the purpose of the diagram, A is acting on the bearing of 90 degrees, B on a bearing of 330, so that's that 30 degrees, and C on 210. So that's going to be 30 there. Yeah. So we can draw a vector diagram of the forces nose to tail to have zero resultant. Okay, so what that means is if we start with A, like so, and then we tack B onto the end, like so, and then it's because it's, and then C, so that's A, there's B, and there's C. Okay, they're all the forces to make into a triangle of forces. And what we've got, let's get some, oh, we don't need to put angles in, they've done it in general here. Okay, so B, just looking at the way they've got these forces here. I'll take these numbers out, those numbers are not so important. Okay, so they've called, right, A, this angle here, that's alpha, that one there, that's beta, and that one there, that's gamma. Okay, now, so that there, what I'm saying, this angle here between the direction of A and B is there, look, so that's a gamma. That one there, that's a gamma. The angle between a B and a C, that's an alpha. And the angle between an C and an A, that's your beta. Okay. So because we've got here angles on a straight line, make 180. This angle here is 180, take away alpha. Similarly with this one is 180 degrees, take away gamma. And that one there is 180 degrees, take away beta. Okay. So now we've got the sine rule. If you remember the sine rule, the ratio of the, look, it's the side length divided by sine of the opposite angle here is equals to the same for another side. The length divided by the angle, B over sine 180 degrees minus beta, C over sine at 180 minus gamma. Okay, now if you remember, we've got at the bottom here, I'll do this, sine A plus B is sine A cos B plus cos A sine B. And if it's a minus there, it's a minus there. So we've got sine of 180 degrees minus, say, alpha. So our A is alpha. Our A is 180 and our B is alpha. And then it's minus cos 180 sine of alpha. Now sine of 180, that one's 0, so that makes that 0. Cos of 180 is minus 1. So this is, I want to do that back, this is what I want here. Minus 1, so it's going to be plus sine alpha. Okay, so it's using that rule that we've seen before. So sine of 180 minus alpha is the same as sine of alpha. So this is 180 minus alpha, sine alpha. 180 minus beta, sine of that is sine beta. Sine of that one is sine gamma. Okay, so the offshoot of all that is that we have a nice formula that we can use if we've got three forces that make a triangle, you see. A triangle of forces acting on a point. Okay. So Lamy's theorem states that if there are three forces acting on an object and these forces are in equilibrium, each force is proportional to the sine of the angle between the other two forces. So let's talk about that then. So here, A, it's sine alpha. Well, if you go back to this original diagram here, look, the alpha is the angle between B and C. So you've got B divided by sine beta. B, or beta, is the angle between A and C. And C divided by sine gamma. Gamma is the angle between A and B. Okay, so we can use it when there are three forces acting on an object and you know at least one of the angles between them. So if you know the three forces, you've got the tops. If you know one of the angles, suppose you know alpha, you've got you've got A divided by sine A. If you know what B is, you can work out what sine beta has to be. And then you can work out what sine gamma has to be. An example. So a block of weight W is suspended by two ropes. Okay, so this is where Lamy's theorem comes in. One rope makes an angle of 30 degrees. So let's call that one, and has a tension 60 newtons. The other makes an angle of 50 degrees and has a tension T. Okay, and then it's got a weight W here. Let's do that with a straight line because that's going to be vertically downwards. Find T and W. Right, T and W. So this is Lamy's theorem. If you've ever got three forces, you can use this. And look, we know... Right, I'm going to do a different colour for all the black is given in the question. I'll do this nice red colour for everything that we work out. Now the weight is acting vertically downwards, so it means that this angle is 180 minus 50, so it's 130 degrees. And that's because that plus that has to make 180. Similarly, that one is going to be 150 degrees, because the 30 plus the 150 makes 180. So now we've got all the angles between, because we can say that that one is 80 degrees. Okay, and we've got a force. That's our clue. I shouldn't really circle that. That's too circle overload. So that one in yellow. So what we can actually write now, turn that back to black. So we can have, we're going to call that T1 and that T2. T1 over sine 130 degrees. Okay, so it's the force divided by the angle between the other two, sine of the angle between the other two. That's going to be T2 divided by sine 150 degrees equals W divided by sine 80 degrees. And we know T1 is 60. So the method is, we're going to work out that one, that's our clue, and then from there we can work out T2 and then W. Right, so T2 is 60, and look for T2. I'm going to look at these two equations here. So I'm going to multiply both sides by sine 150. So it's going to be 60 times sine 150. 60 times sine 150 degrees. divided by sine 130 degrees. Okay, I feel like I need just to change my colour scheme a little bit here. Okay, I can have one of them blue, so this is this first one. Okay, so the blue one gives rise to this. Okay, so therefore T2 is 39.2 newtons. I'll check that properly. So 3 significant figures. Okay, and then the other thing that we can work out, that we need to work out is W. Let's go for a green. So the W with this one. So we've also got that W equals 60 times sine 80 degrees divided by sine 130 degrees. Okay. So let's see if there's a way of summarising this. 60 sine 130, look there. 60 sine 130, that's the known one. And then, so when you want the T2, it's multiplied by sine 150, because that one's there, look. When you want the W, it's got multiplied by sine 80, because that one's there. Now let's get that in green. So W is equals to 77.1 newtons to 3 significant figures. Okay. And that's what the question wants. Right, example 3. A block of weight 60, lies on a rough slope inclined an angle 40 degrees to the horizontal. So it's 60 newtons. So those 60 newtons act vertically downwards. Okay. So as I read the question, like that's just the first sentence, and I draw that as I'm going along. That's really from experience, but I hope you can see where it all came from. Block, the weight always acts vertically downwards. A rough slope, well that means the block will want to slide downwards, down the slope, so that you're going to have a friction, rough. That means we've got a friction holding it up the slope. It's going to want to move that way, but the friction is not going to let it. We've also got a normal reaction between we'll have a normal reaction between the slope and the block. A string is attached to the block. Which passes over a smooth pulley at the top of the slope. Right. Which is attached. Let's just draw a better circle. Which is attached at the other end to a block of weight W, which hangs vertically. So that's going to be hanging vertically, W. So there's going to be a tension in this string. Lots of forces here. The block on the slope is about to slip down the slope, and the normal reaction of the slope on the block is R. The coefficient of friction between the block and the slope is 0.5. So we had that F was mu R in that previous question. I think it came up somewhere here. F is mu R down there. That's always friction. That's always the same. That's always the case. So that's what friction is. And so it says the coefficient of friction, that's the mu, between the block and the slope is 0.5. So the friction is 0.5 R. Okay, let me rub out some of this because it's going to get a bit... And that's that force there. Okay, have we got everything we need, I wonder? find W. So that tension that's in the rope, that's also going to be matched there as well. Right, I think I've got everything there. Right. Okay, find W. So what happens with this R when it's on a slope, and this quite often comes up. Okay, and this looks like this. That can make a right angle triangle there. When we've got 40 degrees there, that's 90. So that angle there is 50 degrees. Now that angle there is therefore 40 degrees because, where are we? Here, there. Oops, wrong thing. Wrong tool. Where's my tool there? There is a right angle. So if that's 40, that's 50. That goes back to being 40 again. So this angle here, because that plus that has got to make 90. That angle there is always the same as that one there. Okay, I'm just going to rub this out again. Friction equals 0.5 R. Right, so what we're going to say here is this is 60. This is the hypotenuse now of a right angle triangle. This here, this is 60 cos 40 degrees. Whoops. And this here is 60 sine 40 degrees. Okay. Yeah. So, what we can do, and what we do is we resolve perpendicular to the plane and parallel to the plane. Okay. So resolve perpendicular to the plane first of all, and we've got that R is 60 cos 40 degrees, which is 46.0 newtons. Okay, so basically what I've done there is I said that one has to be equals to that one, because it's not bouncing up and down the plane, it's just, it lies on it, and that's what's going on. So the next thing we've got to do, we've got to resolve parallel to the plane. Okay, so we've got, let's do a different colour for these. Parallel to the plane, we've got this one, and this one, and this one. Okay, so we've got three forces here. We've got T plus 0.5 R equals 60 sine 40 degrees. So we've got T plus 0.5 times 46.0 equals 60 sine 40 degrees. So therefore T 60 sine 40 degrees, and then a half of 46 is 23, so we subtract that from each side, and you end up with T is 15.6 newtons. Okay, so this is, if you'd like, that one there, that one is perpendicular to the plane, and that one is parallel to the plane. Okay, so now if we look at the other force, so if we look at the force that's hanging, the other two forces, the weight and the tension, we've got T minus W is 0. So therefore T, well, we know what T is, 15.6 minus W is 0, so therefore W is 15.6 newtons. And that is because, let's get a new colour here, this upwards force has to equal that downwards force. So that one comes from there. I'll just put these colours on here. That green, that's those ones there. And then the other one was blue. And they're there. Okay. So that's the blue answer. That's the green answer. And that's the orange answer. I think we've got everything. Find W, done that. Excellent.